So now officially for the camera, good afternoon to everyone. Did you have fun at the seminar that you just watched? It was hard, wasn't it? It was as hard for me as it was for you, so don't worry. Let's start. So this is our functional analysis course, 2019, and today is lecture number 6. We continue discussing the Hyperplane. Okay. So this is chapter 1 of Brezi's book that we are discussing, and I hope this is the last class of chapter 1, so by this weekend you should just go over the rest of the chapter, take a good look at all the examples and the corollaries and the propositions and some of the exercises that are not on the list if you have time. And next week we start discussing chapter 2 of the book of Brezi's and the other classical theorems of functional analysis, the uniform boundedness principle, the open mapping theorem, the closed graph theorem, and slowly we move. Then it will come after this part of weak topologies, weak star topologies, and so on. Alright, let's start reviewing what we proved last class. So last class, we discussed a little bit about this version of the Hyperplane theory in its so-called analytic version. Hyperplane. Some books describe it as the analytic version, as opposed to the geometric version that we're going to see today. And this was a theorem used in a situation where you had E, a vector space, no norm, no Banach space, just a plain vector space, and you had a subspace G. Subspace of E. And you had a functional little g, from G to R. This is your whole space. Right, so you have G as subspace and little g from G to R, a linear function. Right, at this point, it's not bounded, not continuous. Functional, and we wanted to extend this functional to the whole space E, right? And the way that we wanted to do this is provided this: assume that there exists this function P that goes from the whole space E to R, such that it verifies these two properties, right? So P of lambda x equals to lambda P of x. Any x in the space, and lambda bigger than 0, and assume also that this P is sublinear. This is like having an upper bound function, right? And assume also that your function little g loses to this function P for x belonging to G. So if you have this function P that controls a linear functional G on a subspace, then there exists an extension. And the conclusion is that there exists f from E to R linear functional that extends G. That extends little g. And this is one part of the conclusion, right? And this f keeps losing to this upper bound function P. This is important. Okay? And we started to see some corollaries on this. And to discuss the corollaries at the end of the class, we were defining what is this dual space of a vector space. Now, assume that my E is a normed vector space. Assume that I'm on an environment that I have vector space with a norm. Every time that you have a normed vector space, you can talk about continuous functions. Okay, you can talk, and we have seen in the previous class, in the previous lecture, that talking about continuous functions is the same thing as talking about continuous at zero, because they're linear, which is the same thing as talking about bounded functions. Okay, so continuous is the same as boundedness in this setting. And this E space E star, called the dual space, is the space of all functionals, the space of all functions f from E to R, which are linear and continuous. In other words, it's the space of all continuous functionals. Okay, so this is called the dual space. It's obvious that you can take two functions f and g and add them up, or you can multiply by a scalar, so you can add functions, you can multiply functions by a scalar. And this has a norm. The norm of this guy, of f, the norm of a function in the dual space E star is, by definition, the supremum of, say, f of x, where x is x belongs to the space E. This is where f acts, and the norm of x is less than or equal than 1. It's the supremum of, it's the highest value that f of x attains in the unit ball of the space. Okay, so this is the norm in the space is star. And the claim that I left for you as an exercise, I didn't put on the homework. Maybe I should have put this. Maybe take a look here. Maybe I'll put in the next homework. Is that this space E star with this norm is a norm of E star is a Banach space. Norm of E, right? So whenever I will denote the norms with double bars, and I will put the space for which the norm refers to here as an underscript, as a subscript. Okay. When I don't put the space, it should be understood which space it is. Okay. So this is a Banach space. It's nice because even if E is just a normed vector space, this is actually a Banach space. This is with this construction. This is you have to prove that this in fact is a norm. And the fact that this is a norm, just the multiplication by scalar is just easy. You just pull the scalar out, and the triangle inequality here just comes from the fact that the supremum of f plus g in a certain set loses to the supremum of f in the set plus the supremum of g. So it's pretty much a consequence of the definition. So there's not too much problem in verifying that this is actually a normed vector space. But you actually have to prove that it's complete in this norm, that it's a Banach space. And even if this is not a Banach space, this is, and this comes just from the fact that if you take like a sequence of functions that is a Cauchy sequence, you'll be able to produce a limiting functional. This comes from the fact that R here is a field. It's a complete. It's a complete field. So you use the completeness of R to generate this function. So take a look at this exercise and prove that it's a Banach space. Now, this is one comment. Another comment that I wanted to make is that this is the supremum of f in the unit ball. When you are working in infinite dimensions, this supremum may or may not be attained at a certain particular point x. So I guess I put this as two exercises in the homework. You see an example where the supremum is attained. You see another example where the supremum is not attained. Very well. We saw a little application in the end of the last class on this, but let's maybe this duality is very important, okay guys? This duality is very important. And we have already discussed a little bit here in the class when we saw LP spaces. And we will keep discussing this later. So this concept of a space E and its dual space, this will be very important in this class. We'll be talking about this a lot. Now, let me take what if I came to you and proposed to you the following fact? So, let x0 be a vector in E. Okay? Then there exists a function, I'll say it. So whatever, I don't want to say linear functional on E, I'll just say an element f on E star. So there's a functional such that, let's say, norm of f is 1, and this guy here, this norm of f, I'm saying that it's 1, and it is actually attained at my point x0 that I gave you at the beginning. So, and f of x0 is, say, function of x.
Yes, because we can define, we can take the subspace generated by the vector x0, and that's the subspace of A, and then we define a map, which is the map f just sends x0 to the x0, and then by linearity we define the function of this subspace and use Hammana.
Exactly. So the proof is you take the G as the subspace generated by this x0, right? So R times x0, so it's just the subspace generated by this x0. Here you can take a functional which just maps g of t times x0. You just send it to, say, t. So if the vector is t times x0, you just send it to t belonging to here. Obviously this is a functional. Obviously the norm of this g in this space, g star, here is so maybe the x0 of norm 1, so I want maybe I should just take t times x0 if I want, for example. Let's just put it this. So the norm of g is 1 here, right? So I take the guy, same guy. And the function p that you want to construct here is just p of x is just the function module of x. Okay? If x is just the norm of x. So this is a function that satisfies the properties of my p function from the harmonic theorem. I can multiply by scalar and it's sublinear, and it wins against this g in this subspace. So the thing is, I can extend this g. So there exists an f from E to R extending g. So if it extends g, this implies that f of x0 is absolute value of x0 because g of x0 is absolute value of x0, right? And f keeps losing to this p of x, which is absolute value of x. So f of x loses to absolute value of x for any x in my space, right? Therefore, this means that the norm of f in the dual space is less than or equal than 1. If f of x loses to, remember, whenever you have this inequality here, f of x less than or equal than c times modulus of x, this means that the norm of f in the dual space is less than or equal than c. Never have this inequality. In general, what you have is this. This loses to this number times the norm of x. Right? So if this loses to 1 times, norm of x, so this norm is less than 1. But in fact, this norm is equal to 1 because I know that it's attained at the vector x0. The vector x0. Or if you want, since you take in here the supremum over the unit ball, what you would be really looking for is that apply f in x0 over modulus of x0, right? So you should actually be looking at f x0 over, which is a unitary vector now. This is equal to 1. Okay, so the norm of it is 1, and this is attained in the unit vector, which is in the direction of x0. Okay, so the bottom line of this proposition is that if you give me any vector, you can construct a functional in the whole space such that the norm is attained in that vector. Okay? Generally, I told you, if for a general functional, the norm of the functional might not be attained in any vector in the space. But if you give me any vector, you can certainly construct a function such that the norm is attained there. Now, good. Once we have this, you see, now one proposition that is quite useful when we're doing analysis, and frequently you will be asked to use this, or it will be useful for you, is how to relate a norm. So how to relate a norm to the duality map. So if x0 belongs to E, I want to say that the norm of x0 is actually equal to the supremum over f of x0 over all f's in the dual, such that the norm of f in the dual is less than or equal than 1. Okay? You can even put the absolute value here. It doesn't matter because if you have f, you have minus f. So you can put the modulus here or not. But the nice thing is that this supremum is actually attained, so it's actually a maximum of f of x0 over all f in the dual with norm of f. So you can put here also either equal to 1 or less than or equal to 1. Of course, this maximum will always be attained when the norm of f is equal to 1, because if you had something smaller, you can just dilate f and make it bigger. Okay. So note that this expression here and the expression that I just written in the board, they look very similar, right? So the norm of f in the dual space is the supremum that I get applying f of x to x in the unit ball of my original space E. And the norm of a point in the space, norm E, is the supremum of the value of f of x0 when I apply over all functions f in the dual space that have norm less than or equal than 1. So this is a duality state. However, note that this is the definition of the norm of f in the dual space. Okay, this is not the definition of the norm of x0 in E. This is something that is given from the beginning. This is actually a consequence. Okay, so this is while this is a definition, this is actually something that can be proved. This is a consequence of things. And well, how we prove this? Proof. In fact, if the norm of f in the dual space is less than or equal than 1, then f of x0 loses to what? This guy times the norm of x0. Okay, so this loses to 1 times x0. This guy is always less than or equal than this. So you have proved that this left-hand side is bigger or equal than this soup. Right? As you see. You have proved that this guy is bigger or equal than the soup. On the other hand, you have seen that there is a function with norm 1 such that f of x0 is absolute value of x0 from the previous proposition. So, in fact, they are equal. The rest, now use the rest proposition. very important that you keep this sort of duality into your minds. And actually, we have already used this. When we were talking about LP spaces, and we discussed that, okay, the LP norm of a function is a sup of a certain integral of f in G, where G lies in the LP prime space, right? We will see again that this was just a manifestation of this phenomenon here. Because if your space E is the space LP, thus the dual space is just the LP prime. It can be identified, well, if you're not in L infinity, but just the dual of LP is LP prime if P is between 1 and infinity, not including infinity. So, okay, so this is just a manifestation of this thing. We'll come back to this later on in the course when we will actually prove that the dual space of LP is this LP prime. And okay, so this is just to wrap up the discussion that we started in the last class. And keep in mind this dual space and this ways of relating the norm with the duality map. Sometimes I will write f of x0 like a function acting in a point. Sometimes you see in the book f acting in x0 like this. It's the same thing, okay? Just choose your favorite notation and stick with that. Good. So now we're ready to talk about the Hambana and the geometric versions. And the Hambana in geometric versions is essentially a statement that you can just, if you are in a space, you can separate two convex sets by a plane. Okay? So if I am here by a hyperplane, if I'm here on this board, which is a plane, and I drew to you two convex sets, let's just say bounded convex sets, this one and this one. Okay? The interpretation of the Hambana theorem is just that you can separate two convex sets by a line. Okay, so if someone asks you on the bus, what is the Hambana theorem to you? You can just do this picture. Hambana for me is this. I take a ball here, there's always a line that puts one ball on each side. You laugh, but it's actually a true story at IMPA when I was before here. The students had to do, in the PhD, they had to do the qualifying exam, right? So usually a student would do a master's degree, 2 years, and then first 1 year or 1 year and a half of PhD courses and so on, and they would do the qualifying exam, where they would, after the qualifying exam, they would move on to the thesis stage. And the qualifying exam was supposed to be something it was an oral exam of 1 hour and a half, 2 hours, mainly in the subject that you chose for your research, but also secondary subjects that you had to. There was this one student that came to do the oral exam, and there were 3 professors there in the committee of the exam. And the student was very nervous, and very, very nervous, and the professor thought it could start with a simple question. So the professor asked the student, what's the geometric interpretation of the Hambana theorem? So he was just hoping for this picture. The student kind of collapsed. It was the first question, and she didn't know how to answer, and she got annoyed and something, blah, blah, blah. 10 minutes, 15 minutes, I don't know. And then she gave up, and then the rest of the exam just went down from there, and she didn't pass. And then the committee thought there was okay, so usually a student is given the second chance, right? So, okay, you have 1 month to study and come back to the exam again in 1 month. She did that. She studied 1 month, came back to the exam. 1 month later, here's the student, the same 3 members of the committee. The guy thought it was a nice idea to start with the same question. So he started, can you give me a geometric interpretation of the Hambana theorem? And the student's answer was, Damn it, you already asked me this in the previous exam, and I said I don't know. Anyway, student didn't pass and didn't make it to the thesis stage. This is a true story, but this obviously will not happen to any of you. So you have the answer here. But let's see. This was years ago, maybe 20 years ago. So let's first maybe understand what is a convex set, what is a line, and what we want to prove. Okay? So so we are working here E. A keeps being a vector space. Let's keep this notation. Or maybe if I want to put a norm vector space here, just so I talk about continuous functions. Yeah, let me. Yeah, okay, so from the rest of the class, let E be a norm vector space. I'm going to say, well, everybody knows that a set A containing E is said to be convex if and only if for any pair of points, say x and y, belonging to E, I have that linear combinations of these guys, so tx plus 1 minus ty belongs to E for any t belonging to the interval 0, 1. Okay? So this just means that if x belongs to your set and y belongs to your set, the whole line that connects x and y belongs to your set. This is the definition of convex. All right. Convex. Hyperplane. So let's say it's called hyperplane. In this setting will be I will have a linear function, linear in this set. Can you read my letter, or is it too small for you? Is it okay? You have a linear function f, okay, not necessarily continuous, each one at this moment, and point A belonging to real. So I'm going to call this hyperplane. Let me establish the notation here just to keep in mind. So hyperplane H, which is the set of points f, where f is equal to A, is just the set of points x in your space E, such that f of x is equal to alpha. Okay? This is just the definition in the generic definition of an affine hyperplane, right? So you get the linear functional, and then you give me an alpha real. So the set of points such that f of x is equal to alpha is your hyperplane f equals alpha. Okay. Observe that this extends the definition of hyperplane that you have in RD. Right? You just have a linear form, and you make it equal to a certain number, and this is the usual hyperplane in RD. Okay. So sometimes I will denote by H alpha, sometimes I'll denote by just brackets f equals alpha. Let us first discuss when this hyperplane here is actually closed. Okay, because I didn't assume that this function was continuous. So perhaps the first proposition that we want to discuss in the class today is that this hyperplane f equals alpha. And here I have to say that my functional perhaps is not identically 0, right? Because I want to rule out the possibility that my functional is identically 0 and my alpha is 0, such that my hyperplane is the whole space. No, I really want my hyperplane not to be the whole space, to be something of, say, codimension 1. Okay? So proposition 3, a hyperplane f equals alpha is closed if and only if f is continuous. we have seen that f continuous is the same thing as saying that f is bound. Okay? So my hyperplane is closed if and only if f is continuous. Let's discuss this proposition. How will we prove this? You know, in some of these proofs, at this stage of the class, or generically speaking in mathematics, sometimes one of the things that you have to learn how to do is to actually follow the natural steps, or the intuitively what's the right step to do a proof. So this may help when you're doing lots of proof in mathematics. To use all the facts that are available to you, to use all the facts that are in the hypothesis, and to see start and choose a way to start and say, from the way that you start, you kind of continue naturally. Okay, so suppose, for example, I want to prove such a fact, that hyperplane is closed if and only if my function is continuous. So it's an if and only if statement, so I will say that proof, I will prove the reverse statement. If my function is continuous, then this hyperplane is closed. Well, by proving that the hyperplane is closed is like, if I have a sequence of points in my hyperplane, in my set, right, that converges to a point, why that limiting point still belongs to the hyperplane? Well, if I have a sequence of points converging to a point x, since my function is continuous and the value of f of xi is alpha, the value of f at the limiting point is going to be alpha, so alpha is going to be in the hyperplane. So this is kind of the easy part, okay? This is the easy part. Let's put it this way. Now the hard part is the other one. Suppose that my hyperplane is closed, and I want to show that f is continuous. Now suppose that f equals alpha is closed. My mapping here is not 0. But even if the map was 0, it would be continuous. That would be okay. Let's assume that my map here is not 0. So there is a point which is not here, not in this hyperplane, right? So let's call this h. So choose a point x0 which does not belong to h. So you have here your hyperplane h, supposed to be closed, and you chose a point x0. Now, if x0 doesn't belong to this hyperplane h, it just has two options in life. Either the value of f of x0 is less than alpha, or f of x0 is bigger than alpha. Okay? It cannot be equal to alpha because that's h. So let's just pick one of the two for simplicity. The other one is just analogous. So let's pick this one. Suppose f of x is less than alpha. Okay, now comes the point in the proof. How do I go from there? So you pick the hyperplane. It's not the whole space. There is a point outside, and the value is less than alpha, bigger than alpha. So you're assuming that it's less than alpha without loss of generality. So what do you do now? What's the next phrase that I have to say in this proof? I haven't used the fact that the hyperplane is closed yet, right? So now comes a point. So what can I do if I have a point outside a closed set? I can draw a little ball. Yeah, okay. So since my set, so this is what I mean by following the natural steps of the proof. Sometimes you have to know what the next sentence in the proof is because it can only be that sentence, right? So you have a closed set. The complement is open. You have a point in an open set. So there exists some radius r such that radius of r bigger than 0, such that the ball of center x0 and radius r, so let's use this notation for ball, which is just the space set of x and e such that the norm of x minus x0 is less than r. So let me put an open ball, so say less than r, so this will be the open ball of center x0 and radius r. So there exists a small r such that you can place a ball here. That's my picture. Okay, good. So the next line in the proof is saying, okay, so f of x0. So you see this ball in theory, it's supposed to be on the same half of the hyperplane. So if you're looking here at in the blackboard, this ball is in the same side of the line. If you're looking in a d-dimensional stance, this hyperplane would be d minus 1 dimension, and the ball would be on one side. So we have to make this mathematical, right? So the claim is that now we claim that f of y, for any y in the ball, is still less than alpha. For any y in this ball. And again, let's go by contradiction. If not, there would be, this is y0 in this ball with, go ahead.
We didn't have both any condition on the ball. We should say that the intersection with h is empty, right?
So such that b or not intersect h is empty. Or, yeah, contained, if you want contained, and h contained. Thank you. Okay? So if not, there exists a y0 in the ball such that f of y is actually bigger than alpha. Why can't it be equals to alpha? Because I'm already assuming that the ball does not intersect h. So if it's not less than alpha, it should be bigger than alpha. But now it's the point to use that the ball is convex. So you have here inside your ball, you have x0, you have y0, right? F of x0 is less than alpha, f of y0 is bigger than alpha. So this f of a convex combination, tx0 plus 1 minus ty0 by linear. This is a point here that belongs to the ball because the ball is the simplest of the convex sets. This is t f of x0 plus 1 minus t f of y0. And if you want to reach a contradiction, you want to make this guy equal to alpha, you have to solve for t, right? Now you solve for t and you find, what is t here? T is, move everybody to that side, so a minus f of y0 divided by f of x0 minus f of y0. Is that correct? This is the t. Generically, this thing is negative, so let's multiply by minus up and down. So it's minus alpha plus this, minus this. Now numerator and denominator are positive. And observe that this guy here is between 0 and 1. So this is positive because f of y0 is bigger than alpha. Positive. So t is bigger than 0. And why is it less than 1? It's less than 1 because f of x0 is less than alpha. Okay? So this t, this particular t between 0 and 1, will create a contradiction. You will find a point in the ball such that the value of f at that point is equal to alpha, which is a contradiction because this ball is supposed to be outside. So we have proved mathematically what our intuition has told us, that the ball lies on one side of the plane. But this is essentially the statement that we wanted to prove. Now, therefore, we have proved that f of, say, we can write the ball, one way to write the ball is x0, the center, plus r times z. We have proved that everybody in the ball, the value of f is less than alpha for any z in the unit ball. Say the ball 1. This is just set where z is less than 1. Less than 1. So for any z in the unit ball, I mean, you can go, maybe you can go from the beginning right here. If you want closed balls, you can just choose r over 2 instead of r. It's no big deal. So for any so what does this mean? This means that f of x0 plus r f of z is less than alpha, which means that f of z for any z in the unit ball is going to be less than alpha minus f of x0 over r. See? So for any z in the unit ball, the value of f of z loses to this number, which is a fixed number, right? Alpha minus f0 is a positive number. R was a number, fixed number. Okay? So this means that f is bound. And in fact, the norm of f loses to this number here, because I'm evaluating f at any point in the unit ball. Okay? You can even write like norm of f loses to this number. With an equal, less than or equal here, because it can get close to this number. Okay, so this is okay. Good. So this is the statement that now we have set our notation. You're looking at me with a face.
So what if the inequality is the other way?
What if the inequality is the other way?
Yes.
What do you mean? This is plus.
Yes.
If you started with this case,
Yes.
If you start with the x0 plus rz is bigger than alpha, then r is bigger, but you'd have a negative numerator, right?
If we multiply minus and f is linear.
In the other case, you would have f of c, you'd have this, right? So you take f of z bigger than alpha minus f of 0 for r. But the numerator is negative. In the other case, in this case here, where f of 0 is bigger than alpha, this numerator will be negative. So you multiply everybody by minus 1. So you get f of minus z less than f of x0 minus alpha over r.
Or we can just consider minus x in all.
And multiply inequality.
Yeah. So it's the same thing. Okay. All right. So from now on, whenever I talk about a closed hyperplane, I mean that I'm taking a hyperplane associated to a continuous or bounded functional. Good. So the theorem is the following. So this is the Hambana theorem in a geometric version. Let's see. Let E be a normal vector space. Let A and B be subset B two convex subsets of E with A intersection B equals the empty set. So two disjoint convex subsets of E. Assume that A, one of them, let's say A, is open. Assume that one of them is an open set. This is an important assumption of the theorem. Otherwise, it will fail. The conclusion is that then there exists a hyperplane a closed hyperplane, let's put it this way, f equals alpha that separates these sets, separates A and B. that is that f of x is less than or equal than alpha is less than or equal than f of y for any x in A and y in B. Okay, so f of x will be less than alpha for all the points x in my one set A, and f of y will be always bigger or equal than alpha for any y in the other set B. So there's a hyperplane that separates them. Note that here I'm just taking less than or equal to. It can be equal to alpha, it can be equal to alpha. So this is the notion of separation, but not strict separation. So if we have time later in this class, we discuss how to even strengthen this theorem a little bit. If you have your sets, then you have the same statement, but then you have to assume that one of the sets is closed and the other is compact. And then you will be able to strictly separate them. But let's...
Are we fixing f from the beginning that works for all these two sets, or f depends on this choice of...
No, naturally f and alpha depend on the two sets, A and B, okay? So the sets are given, then there exists a closed hyperplane, which then you have to tell me which f is and which alpha is, that separates the sets. Okay? Remember, and then geometric interpretation is this. Okay? This is what you take from today's class. A and B. X equals alpha. All right. How do we prove this? The proof of this is very nice, very elegant, and we will use our analytic version of the harmonic that we proved in the last class. But let me first, we're going to need two preliminary results to prove this, I guess. Let's see if I remember. If not, you guys will help me. Okay, so let me define this so-called gauge function or Minkowski function of a convex set. So let's see be contained in E be a convex set. Assume that 0 belongs to C. Assume that we have a convex set and your 0 of the vector space belongs to C. So let me just do it here. This is your convex set and assume that 0 belongs to C. This is your C. Okay? I want it to be open. So let C be an open convex set and assume that 0 belongs to C. So if 0 belongs to our convex set, then there is a little ball that keeps belonging to this open set, right? And I can define the following function. Define for each x in the whole space the function p of x, and the name p here is very suggestive of what we have done. P of x is going to be the infimum over all alpha positives over alpha such that, say, x over alpha belongs to my set C. Okay. So my x is fixed. So if you take an x right here, I'm trying to define this function p of x as the infimum of all real numbers alpha, of all positive numbers alpha, such that x over alpha will finally fall inside my set. Of course, if alpha is huge, if I set alpha to infinity, then x over alpha will be very close to 0, and I know it will fall in my set. Okay, so for alpha very big, I know I'm inside my set, and I don't go out again, right? Because once I'm inside, if I'm dividing by alpha, I will keep inside. Right? So from a certain point on, I will always be in my set. The thing is to find the infimum of these guys such that I fall into my set. So this is sometimes defined as gauge function of C, sometimes called Minkowski function of C. It's not in fact a function, it's not linear. As we'll see, this function P is actually sublinear, as we shall prove. Okay, so this is a well-defined thing. So with respect to this object P that we just defined, let us prove the following. So let us prove the following. Proposition.
Sorry, but what is a gauge? I mean, why is the usage of this term?
To be honest, I don't know. To be honest, this is one of the mysterious words in mathematics that pop up anywhere with slightly mysterious meanings to me. So maybe if you know more mathematical physics or differential geometry than I do, you can ask Claudio Arezzo, why do they use this gauge function, gauge word? What does it exactly mean? You know? It's very mysterious to me. So it's like the word quantum. They tend to use for a lot of things. I bet there's one original significance, but then they extrapolate and then you see quantum in a lot of things. It's a rule of thumb. I mean, whenever I see quantum engaged in the same sentence, I just go away. Say, okay, I don't understand. I'm kidding. But I get scared. Anyway, doesn't matter how we call it. The important thing is how we define it, and we understand the definition. So proposition is, let's try to prove the following things about this function. P of lambda x is equal to lambda P of x for lambda positive. Very reasonable, right? So P of x plus y loses to P of x plus P of y. Let's prove the sublinearity. 3. What else do I want to prove? There exists a constant m bigger than 0 such that P of x is less than or equal than m times absolute value of x. And number 4, the set C is the set of points x in P such that P of x is less than. Wow, 4 beautiful statements to be proved there. Let me prove one of them, and then I'll ask for your help for the other 3. I'm going to prove number 1. Okay? So if I go and take my point x and multiply by lambda x is right here, in order to make lambda x fall and divide by somebody and fall into my set, I have to just multiply lambda times whatever it was dividing before, right? So the number 1 is pretty much okay from the definition. Okay, this is okay from the definition. If you understood the definition, you understand that this proves number 1. Okay, so which one do you want to prove next? That might be a little bit more tricky to prove. Let's leave number 2 for the end. Let's prove number 3. Number 3. Why there exists a function such that P of x loses to m times the absolute value of x? Do you think this is a consequence of what? I am going to draw here for you. This is just a consequence of the openness, right? This is a consequence of having this little ball inside the set. So since it's open, we know that there exists, let's say, a little ball of center 0 and radius r. You can even make a closed ball. Right? So this is the set of x, is that absolutely fine. It's less than or equal to r. Right? That is contained in my set C. Okay. there's a little ball around the origin that is contained in my set C. I'm using bar here to denote the closed box. I'm taking less than or equal than R. Now, since this is true, so this means that for any x, my set E, if I just take x and divide by the absolute value of x, this will have norm 1, right? And multiply by R. Okay, so if I just consider this, x times R over absolute value of x. So this has norm 1, this has norm R. So this is inside this ball, so this belongs to, this guy belongs to C, because it lies inside this ball. Okay, so this is the same thing as taking my x and dividing by this number, this alpha, x over R. Okay? So I'm taking x, dividing by this number, I fall inside my C. So this means that the P of x, which is the infimum of such numbers, so if I'm dividing by a number and I'm falling inside my set, this means that P of x is smaller or equal than this number. So this means that P of x is smaller than or equal than this. And here's your M. M is just one of our.
Sorry, what's 4? What is the statement of 4?
4 is that the set itself, C, is the set of points in the whole space E that have this function P of x less than 1. Let's see, 4. I want to prove that the set C is the set of points that have P of x less than 1.
So C is in this set. C is in
Yeah, we're going to prove both inclusions here. So y is, so if x belongs to C, so if a point is in C, I can, alpha 1 works.
So the infimum is this.
The infimum could be equal to 1, but here I'm saying that it's strictly less than 1. I'm going to do this. So if x belongs to C, since the set is open, there exists an epsilon bigger than 0, such that 1 plus epsilon times x still belongs to C. Do you agree? So I can just multiply, dilate a little bit, right? So if x is a point in C, since it's open, I can just go a little bit more there. Now I'm okay. So if 1 plus x, epsilon times x belongs to C, this means that P of x is less than or equal than 1 plus epsilon, because this alpha works, right? Which is less than 1. So you're proving that everybody in your set C has the P less than 1. So you're proving that C is contained in the set. Okay, so this proves that C is contained in the set. The P of x is less than 1. Now let's do, so this is one way. Now let's do the other way, the other inclusion. So this is one inclusion. Let's split it this way. Inclusion like this, inclusion like that. Let's take a point x in the space such that P of x is less than 1. So take x belonging to the space such that P of x was less than 1. Well, if P of x is less than 1, this means that 1 works, right? So this means by definition, alpha, if I take x over alpha, I belong to C. So it's the infimum. So if the infimum is less than 1, this means that if I take alpha equals 1, I fall in the set. This means that alpha equals 1 works in the sense that x divided by 1 belongs to C. This is the rest of it.
convexity.
Not yet. Very good observation, right? So this was independent of convexity, right? Maybe to say that the ball is somewhere, I don't know. This we just use the open property. Sorry, say that again. We're going to use now for number 2.
For number 2, we need
The convexity, yes. We're going to use convexity, right? But good catch. Keep an eye for that because this is a hint of what we need for the proof, right? So, so finally we prove 2. I want to prove the sublinearity of this. So what I do is that I just take my 2 points here, x, y, and I'm going to take here the x plus 1. Go ahead.
After force, I think it's trivial because C is an image of convex function, and so if C is convex, no, C is convex. I mean, image of function is convex. We can say it's convex function.
Say that again. So C is a
Just
convex set.
image of function. I mean,
Image of if you have a function, you want the image of a convex set.
yeah.
This can be anything, right? If you don't tell me more about your function. But this is not so hard. It's just from the definition too. I mean, P of, let's say, what is P of X? So by definition, so take epsilon bigger than 0. Your favorite epsilon. So by definition, so P of X was an infimum of alpha such that those things hold. So we found the set. So if you take X and you divide by P of X plus epsilon, so if you add up a little bit to this inf, you should fall in the set, right? So this belongs to C. So does Y over P of Y plus epsilon. This belongs to C too. Okay? So this is your set X, and you divide it by somebody to fall here in the set. Maybe just entering here in the right, barely entering, that's okay. And you're taking Y and dividing by somebody entering. And the idea here is to just take X over Y and look some sort of linear combination here if you want. So this guy belongs to C, this guy belongs to C. Any linear combination of them, so P times X over P of X plus epsilon plus 1 minus P times over Y times Y, P of Y plus epsilon. This belongs to C, right? So now let's make a reasonable choice of T. So what I want is to get a reasonable choice of T to make my numerator X plus Y. So this is what I want. To make my numerator X plus Y. So I think I need, so what do I want here? T times this, so minus T times this.
P of X plus epsilon over P of X plus P of Y plus 2 epsilon.
Say that again. P is going to be
P of X plus epsilon.
P of X plus P of Y plus
No, this is the numerator. This is the denominator.
Yeah, at the end I want this number to be,
Yes, so it's P of X plus epsilon over their sum.
you want this?
Yes, over their sum.
Is that so?
Yes. No, over 2 plus 2 epsilon.
Yes, exactly. So take this T. When you take this T, this will cancel here, and you get just X in the bottom. 1 minus T will cancel here, you get just Y in the bottom. With this T, this guy here becomes X plus Y over P plus P of X plus P of Y plus 2X. This belongs to C. this choice of t. Okay? So x plus y over p of x plus p of y plus 2 epsilon belongs to C. So x plus y divided by somebody belongs to C. So this means that the p function at this point has to be less than this somebody here. So this means that p of x plus y has to be less than or equal to p of x plus p of y plus 2 epsilon. Since this holds for any epsilon that I took in the beginning, this must be true.
But how do you know that this p is greater than 0?
It's definitely greater than 0. This p function is always non-negative, right? P function is an infimum of non-negative numbers.
Okay.
And it's obviously non-negative, and it's obviously less than 1, because the denominator is p of y plus epsilon plus this guy.
We always assume that p is non-negative.
By definition, right? P was an infimum over,
Sorry, yes.
p of x was an infimum over non-negative numbers. Okay, this concludes the proof of this fact. So you already see where I am trying to lead you from this, right? This p function will play the role of the p function that we had in the analytic version of the Hambanian theorem. I guess what I want to do now is to perhaps, okay, is everybody okay with this proof? Very nice, very geometrical. Have to choose some details on the way here, but there is not too much sophisticated, but very, very interesting. Now let's see. Can I erase here? So the other proposition that I wanted to make, maybe, proposition 5, is to prove the geometric version of the Hambanian in a very particular way, where one of the sets is just 1 point. Okay, so let C be convex, open, C contained in E, right? So let C be contained in E, be convex and open, and let x0 be a point outside C. So you have a convex and you have a point outside C. What do I want here is to show that I can divide by these two guys. Let's see. Yeah. C non-negative, right? So whatever. I should assume that it contains the origin. No, not necessarily. Okay, so then, the conclusion is that then there exists a continuous linear function, so I got into dual, such that f of x is less than or equal than f of x0 for any x in C. Okay? So the thing is, if you have one set C here, and 1 point outside, there is a functional that separates these two entities, the convex set, the open convex set, and my point. So this is a particular case of the theorem that we want to prove, where one of the convex sets is just 1 point. Right? How would we prove this? So let's see. Let's think about how we could invoke the version of the Hambanian theorem that we already know to prove this statement. So first of all, without loss of generality, we may assume that 0 belongs to the set C. I just do a translation. Okay? So if I just take my picture here, 0 is right here, and I take the center of C, wherever the convex set is, whatever point it is, and do a translation to 0, this won't change, right? For any linear function, any linear functional, I'll be subtracting both the same thing on both sides. Okay. So without loss of generality, we may assume that 0 belongs to C. We may assume that this is 0. Just by translation. Now, how do I use harmonic here? So you kind of have a little bit of the ingredients of the version of the harmonic before, right? We have the P function. The P function will be the Minkowski function of this set C. Now I have to define a functional little g that I want to extend. Probably it will be on this space here. I call it the space generated by x0. So let us consider, let's see if we are correct. So this is the only possible way to go. Let us consider the subspace G being R times x0. And let us consider a little g of x and little g in this space, g to R, by putting g of x, g of t x0 as just being
T if
should be put maybe t times norm of x0. Is this okay? Let's see if we put just t or t times norm of x0. Okay. Suppose we have this. Now I would like this g to lose to the function p, right? So I would like g of tx0 to lose to p of tx0. So this means that g of t by dilation, g of x0 would have to lose to p of x0. P of x0 is bigger than or equal to 1 because x0 is not in my set, right? So I would have to make g of tx0 to be 1, for example. So this is not here. So let's just make g of tx0 equals t. This is my functional. Now, okay, so now with this, now observe that g of x0 itself, which is 1, loses to p of x0. By the previous proposition, p of x0, since x0 is not in the set, is bigger or equal than 1. So, okay, so we're using item 4 of the previous proposition. So this obviously implies that g of tx0 loses to p of tx0 for all t real. Obviously for t positive, it's just a consequence of the dilation. And if t is negative, well, p of minus tx0 is still positive. It's p of somebody, p of any point is still positive. And g of minus tx0 is just going to be negative. It's minus t g of x0. It's minus 1. Okay, so this actually holds for any real number. All right. Good. So here's your function g, your linear function on this subspace. It loses to this Minkowski functional p by the property 4 of the previous proposition. And by harmonic, we can extend this guy. Hopefully, it will lead us to what we want. Now, by harmonic in its analytic form that we proved, there exists f that extends g. This f extending g. Right? Does this function f does the job? So it's a linear functional, right? And because of property 3 of the previous proposition, it loses to a certain constant times the absolute value of x. So property 3 of previous proposition implies that f belongs to actually the dual space. It's a bounded linear function. Because it loses to p and p loses to, well, p of x loses to m times right? So f extends g and f of x loses to p of x. So f is actually a guy in the dual. And, well, of course here, so f of x loses to p of x for any x in C. F of x loses to p of x if you are in C, p of x is less than 1, right?
Yes.
And 1 is just, well, 1 is just g of x0, which is f of x0. For any, yeah, this concludes the proof. So the result is actually stronger than what I had. So it's actually strictly less. Is that okay? Yeah. This is the proof. And here I'm using again property 4 of the previous proposition. Okay? Are we good? So, okay, so now we're ready to the proof of the theory. So we have proved two facts, right? So let's recall what we have proved. We have proved these properties about the Minkowski function of a convex set that's open and contains the zero. And we have used this to prove our geometric harmonic in this easier setting of having one convex set and just one point out. Okay? Here's the state. Now let's go back to the general situation where we have two convex sets, A and B, and A is open. So A is open. So the idea here, the very nice idea, to somehow make use of this situation where you have just one point, is to consider the set C is as the difference set, A minus B. This is not A minus B as sets, but it's just the sets of points A minus B with A belonging to A and B belonging to B. Here's the set of the differences. So consider this set C. Now I have some claims to you. I have some claims that this set C is convex. Does everybody agree that this set is convex? Because if I take 2 points in the set, so it's A1 minus B1, and then A2 minus B2, and I take a linear combination of these two guys, I can just take a linear combination within A and within B, and I'll get that this guy is a guy in C. So this set is convex. This set C is open because the set C is actually a union of A minus, say, B when B belongs to B. So I can just take this huge set C as a union of A minus each element of B. So A minus one element of B is just a translation of A. So this is an open set. Since A is open, a translation of A is open. And any sort of union of open sets is open. So this union doesn't have to be countable or not. Union of open sets is open. So the set C is open. And the third thing is that 0 does not belong to C. because A and B were disjoint to start with. Okay, so I'm using here, I'm already using the fact that A is open, I'm already using the fact that 0 does not belong to C. Well, I'm observing. Now let's use the fact that 0 does not belong to C. So you have a certain convex set C now, so you are in the situation where you have a convex set here C, which is open, and thus it has a certain particular point out. And this particular point is the 0. Now we're going to invoke this. So let me erase here. Because the proof, I translated and put the 0 inside, but I can actually use with the 0 outside. So, by proposition 5, what we have? There exists F that separates C and 0. In other words, F of x loses to F of 0 for any x in C. Well, but if F is a linear functional, how much is F of 0? It has to be 0, right? This means that F of x loses to 0. But any point x in C is of the form A minus B. So F of A minus B loses to 0 for any A in A and B in B. So this means that, since F is linear, F of A loses to F of B for any A in BA and any B in BB. And we're going to use a trick that we used an observation that we used in the last class, right? So if you have an inequality, F of A less than, you have a function, there exists this nice function in the dual that has this property. F of A loses to F of B for any A in A and any B in B. You're going to take the sup on this side and the in from this side. This means that the infimum of F of A, the sup F of A with A in A loses, and it's less than or equal. We're going to have to put less than or equal here because these guys could approach. Then the infimum of F of B when B belongs to B. Okay? Finally, you choose alpha somewhere in between. So you squeeze your alpha. So finally, you just choose alpha such that the sup of F of A when A is in A less than or equal than alpha, less than or equal than the inf of F of B when B is in B. And that's your alpha.
That's a wonderful proof.
Huh?
Wonderful proof.
Wonderful proof, right? Wonderful. Wonderful. Can you give me a geometric interpretation of the harmonic now?
I don't know.
Okay, you have 1 month to prepare.
Yeah. Bene. 3 minutes. Let me just comment on the 1 second version of this. Past 5 minutes of the class today. That's fine.
I'm just curious. So why is the first version called analytic? There is no any analytic structure with that.
Well, analytic not in the sense of complex analysis, but analytic in the sense that it's not geometrical. It's not geometrical. Analytic in the sense that it's in the complement of. Well, maybe. I mean, again, harmonic. Let me just comment on this particular situation where you have, say, let's see, what do I have? I want here now the situation, same situation as before, A and B contained in E, non-empty. Convex subsets. Now I want the situation where A is closed and B is compact. A is closed and B is compact. Okay. Then there exists a closed hyperplane H F is alpha that strictly separates A and B. That is what is strictly separates. So there exists epsilon such that epsilon positive such that f of x loses to alpha minus epsilon, and f for any x in A and y in B. Okay, so now not only f of x is less than alpha, less than or equal than alpha, but it loses to alpha minus epsilon, and f of y for y and b is bigger than alpha plus epsilon. Okay, so now you're in this situation where you have to strictly separate these two guys, A, B. You want really somebody that has some distance here. The proof is pretty much the same. Let me just see what I want. Yeah, so proof. The idea is to consider again the different set. So C equals to A minus B. And the difference A minus B with A belonging to A and B belonging to B. Now we have seen that this set, being the subtraction of two convex sets, is convex. We have seen that 0 does not belong to this set. Now it's not open anymore. Okay, it's not open anymore. Because I'm not assuming that none of the sets is open. But, however, this C is actually closed. And how do you see that this set C is closed? Well, here is the modal argument, right? So I want to prove that it's closed. So any sequence of points, any convergent sequence in the set C should converge to a limit guy that is in C, right? So take a convergent sequence of points in C. So points in C are of this form, AI minus BI for certain indices I. Assume that this converges to a certain guy, let's say C. And you want to prove that this little c is in the set big C. Okay? So AI and BI is a certain sequence of points here converging to a point C.
B is compact, so BI has a convergence of C.
The only thing you can use at this point now, so the next step has to be this one, is the fact that B is compact. So every sequence BI in a compact set has a subsequence that converges. So you can assume that BIK converges to a certain B. Well, but if BIK converges to a certain B, then IIK minus BIK, that keeps converging to C, right? So this means that AIK has to converge to a certain guy A. Well, and B is in B because it's compact, and A is in A because A is closed. So this means that C is A minus B with AA and B and D. Okay? So this set is actually closed. Now, good. Now, with this information at hand, you have now your set C, which is closed right here, and 0 is out. Well, if 0 is out of a closed set C, the only thing we can do is to put a little ball here. So there exists a little ball centered at 0 of radius r. Let's make it even closed or open such that the intersection with C is empty. Let's make it an open ball. Okay, this is an open ball centered at 0 that does not intersect C. Okay, now I can use the previous version of the theorem, because I have two convex sets, C and this ball B, BR. One of them is open. Okay, so by the previous version, there exists an f equals alpha that separates C and this little ball of radius r centered at the origin. So this means that what? F of x is less than or equal than alpha, which is less than or equal than f of, let's say, rz, okay, for any x belonging to C and any z belonging to the unit ball. Are we okay? Now let's open this up. So a point x in C is a point of the form a minus b. This loses to alpha, which loses to r f of z for any z belonging to the unit ball and any a belonging to a and b belonging to b. Beware to not make a confusion between the ball of radius r, b1, which is b of 1, and the center. Okay. Well, I don't even need this alpha here, so allow me to take it off. So let's just put this. Okay. Now what I'm going to do is, this is a number. So, okay. Okay.
Because f is bounded, we can remove f of z. So. Or just put the supreme.
Yes, okay. So this loses to this for any z in the unit ball, right? So, of course, this is going to lose to r times the norm of f. Are you guys okay with that? It's certainly going to lose to that, because this loses to that. Now it's okay. Now I'm going to take this guy, which is now a fixed number, and I'm going to shuffle things in this way. So f of a minus this guy divided by 2 loses to f of b plus this guy. Do I want to do this? No. I want to actually do better because I'm losing, right? So f of x loses to this guy for all z's in the ball of radius, in the unit ball. So since this is an upper bound, I'm going to choose the z that gives me the smallest possible. So this actually loses to this. I can get the z, just pull the r out, and I can get the z that gets me as close as possible to minus the norm of f in the unit ball. Okay? Since this has to hold for all z's, this has to hold too. Pay attention to that. So actually I want here a plus, and here I want a minus. Okay?
We don't need to do that.
And again, the same trick. This holds for all a's in A and all b's in b's. This is fixed. This is a fixed number, which I'm going to call, this is going to be my epsilon at the end. I just take the supremum over all a's and a's of this side, f alpha, plus this, let me call this epsilon, which is less than or equal than the infimum over all b's and b's of this f of b minus epsilon. Okay, this is less than or equal than this, and then all you have to do is choose an alpha that fits in between. Just choose an alpha here. Okay, so when you choose your alpha here, then f of a is going to lose to alpha minus epsilon for all a, and f of b is going to win against alpha plus epsilon for all b's and b's. Good? All right. So that's enough for today. That's enough for chapter 1 of Precise, what I wanted to talk to you about harmonic. There are other nice propositions and observations in the book, so I really strongly suggest that you take a look at the whole chapter 1, some of the exercises, and I go over the homework set over last week. Let's make the second homework due for next Friday, okay? So we got the homework set number 2 is going to be due for next Friday. You have 1 week to think about it. Is that okay? Guys, have a good weekend. We stop it here for today.